Okay, so we should be ready to start soon. Just before we start properly, can I just check that people in the Zoom can hear me? If someone can just send a message. That's great, right. Okay, so we will start now then. Right, so welcome everyone to the fifth annual workshop on neural architecture search when my slides decide to update. There we go. This workshop is run in conjunction with Newcastle University, Durham University, the University of Edinburgh, and Baidu. My name is David Towers. I'm going to be the organizer and the runner for today. However, we do have a lot of people behind the scenes who helped with scheduling and stuff. So this year for this workshop, we have a brief tutorial to introduce NAS. We use this because people in the past have came see like our keynote speakers or presenters, and a lot of them are a bit information dense with keywords that people outside the field aren't necessarily certain. So we're going to start with a roughly 35-minute introduction to that. We also have Radu Marculescu as keynote speaker, who's going to talk about zero-shot NAS. And we have 6 accepted papers, each with a presentation and an optional poster. What I have found out today is that CVPR has, for some reason, decided that while the workshop is here, the poster session is over in the other building. So we'll see what we do about that. So before we get in, I would like to ask you if you don't mind, if you can scan the QR codes and fill in our online form. We use that to see we use that to show our supervisors and superiors that people do actually come visit. It's worth for us to running it on, and our mailing list will keep you up to date for other workshops that we run and NAS competitions, which I will talk about towards the end of the workshop, as we are running one at another conference later in the year. So we'll go over our schedule today. So we have our welcome, which is just going to be over another 3 minutes once we get through the schedule. And as I said, we have our brief introduction to NAS. We have Radu Marculescu as our keynote with zero-shot neural architecture search challenges, solutions, and opportunities. As I said, we have our post session at 3 until 3:50. As I said, this is in the other rooms. This is in the Arch building. Don't ask me why. All posters are over there, and then they put some of the workshops over here. But our posters are 338 to 355. Although some of our presenters have got their posters online, and some opted not to do a poster and instead just give their talk. But it's as you go in, it's on the left hand. You have as you go in, there's a row of boards on the right, and then you've got the middle section of boards. If you go up the aisle in between, it's around in the middle. And after that, we will hopefully we'll have most of you back here for our 6 paper presentations, which would be about 10 minutes each, with about 5 minutes for questions. And then finally, we'll have a 10-minute section for closing remarks. So without further ado, we'll get on to the brief introduction to NAS. And so as a brief overview to this presentation, as I said, it's going to be about 35 minutes as an introduction. We use it because people sometimes come in and end up being too complicated, or not necessarily complicated, but just too unfamiliar with them, and this can lead to confusion. So we want to try and get people onto a similar page so the workshop can be enjoyed by as many people as possible. This presentation was designed with image classification NAS in mind. That is, after all, we are at a computer vision conference, and that is mostly where my research figures, but NAS can be applied in other areas. The original NAS paper itself worked on text prediction. A lot of what I said will apply, but just there might be some specific examples or bits that are for the image classification side of NAS. And basic understanding of machine learning is expected, although we do briefly talk about what a neural network is, as that's kind of fundamental for neural architecture search. And so without further ado, what is a neural network. And if you look online, you'll see the definition is it's a mathematical model which we use to approximate a function rather than having to make it ourselves. And instead of having to hard code something, we can just give it to the computer to figure it out. And this is the main concept of neural networks and pretty much why machine learning as a field exists, and we're seeing the rise of it, is we can use it instead of having to hard code something. For example, with self-driving cars, Tesla pioneered this, although that's maybe sort of slacking in recent years compared to other competitors. But it's very hard to take an image and say, oh, there's a human on the road there. But it's very easy to draw a box around a human, say, there is a human here, figure out what human in this image is. Or at least it's easier than, as I said, hard coding it. So when we talk about a neural network, we need to talk about neural architecture. This is how the network is made up. This is what we give the computer and tell it on how to connect everything together. And so very often we have layers of neurons which are all connected by edges. So in the example on the screen here, we have like a very simple multi-level perceptron, very basic form of machine learning network, which has 5 layers, an input, an output, and 3 hidden layers, and a fully connected mesh topology. And basically each neuron takes input from the previous layer and forms a weighted sum. And then we apply an activation function, which is the output for the next neurons. And in conventional neural networks, this is mostly what the computer figures out. It tries to figure out what weights make the optimal sum, which applies the activation function, and then which makes an optimal output. And so we use a backward propagation to cascade backwards in order to find an optimal network or train the network. The problem is there are an infinite number of different network architectures. So this is an image of GoogleNet, which is one of like the off-the-shelf ones that you can download from the TensorFlow or the PyTorch libraries and then then fine-tune for your own problem. And you can see it's a very different structure to the one that I showed earlier, the multi-layer perceptron. And it's not just that it's got a different shape, it's got a different like connection topology. It's just also got different types of layers in between them. Different topologies, different layer types, the different hyperparameters you use, all of these affect the final outcome, and all of these are part of your neural architecture. And different architectures perform better on different data sets, which leads us to ask is what is the best network to construct for any given data set? And that's a hard problem to solve. So if you have the knowledge, you might be able to transfer techniques from one data set to another. If you work on ImageNet and you make a really good network for that, for Cypher10, which is a small data set of like a similar complexity, you might be able to transfer some techniques that you found or network decisions that you used and apply it to that. And there are many very good neural networks available off the shelf, which you can find too. GoogleNet's one of them, ResNet's another one, VDG, Inception. But the question that we end up asking is, do they give you the best result? And for a lot of cases, you don't need the best result, you just need a pretty good result. So then that leads to the next question is, are they within 5% of the best result? And there's not really any way to know unless you know what the best result is. But as we said, there's an infinite space of possible architectures. So we don't really know what the best is, or we don't really even really know what the best weights are for an off-the-shelf model. And so to find all this out, it takes time-consuming trial and error. You try a network, see what results that give you. Then you need to fine-tune. You might change the hyperparameters, find out how they affect the result, and do that again and again. And this is where neural architecture search comes in. So instead of using an expert's time and knowledge, or in my case, my time and knowledge, why don't we automate it? And so neural architecture search is a way to automatically search for good neural network architectures. Instead of manually editing the model and testing it, we can use the same principle of a neural network itself, where we give it an input and an output, and it finds the best weights, where we give our neural architecture search algorithm an input and an output until it finds the best network, which gives the best output. And this allows bespoke neural networks to be generated without needing an expert's time or knowledge. Now, before we go a bit further into talking about neural architecture search, we want to talk about what we have identified as the 3 basic parts of NAS. This is pretty much every NAS network we can split into these 3 parts. there's the search space, and this is all the possible networks that your algorithm will consider. Modern day NAS algorithms like to use benchmark search spaces. So that is stuff like NASBench 201, NetsBench, or any other benchmarks. But the more interesting part of NAS, or the part which people like to, which people do write more papers about, is the search policies. This is how you search through NAS, through the search space. So this is like the original NAS algorithm itself, or the more modern ones like BetaDARTs or BOSNAS or ENAS, although that one's not too modern. And you can break the search policy into two phases. So that's the search phase, which is the part which actually searches through the search space, that finds the architectures. And then there's the evaluation phase. This is the part where you take your search architecture, you fully train it, and you get your test result, and you use that and say, okay, this is our results. And the final part, although we won't go in too much into this in this presentation because it's very general amongst machine learning itself, is the data policy. This is what sort of augmentation you do with the data before you feed it into your network. So stuff like cutout or auto augment. It's very important in machine learning as a whole, but as I said, it's not very specific to NAS, so we won't cover it too much in this talk. So I think at this point it's probably a good idea to talk about the original neural architecture search algorithm, which was made by Zoff and Lee in 2017. And basically the main idea of it was that they realized that neural network architectures can be encoded into strings. And this is the image they give in their paper where they show that, where they encode, where they tokenize the number of filters, the filter height, the stride height, stride width, etc. for each layer, and feed that into a recurrent neural network, which is a neural network that's very good at doing text prediction. And therefore, using reinforcement learning, we can generate a architecture using the tokenized inputs, fully train it, get its result, feed that back into the controller RNN as a reward signal, and then that will generate a new one, and we repeat this cycle until we get the best architecture that the RNN can give us. And so effectively, we can use machine learning to optimize machine learning. The problem with this method was it wasn't efficient. The original NAS algorithm took 28 days on 800 GPUs, which were all about 61 GPU years. And since that's not viable for most people, it probably won't shock you to know that this was done by the team at Google. It's just not a reasonable timescale to remove the need for manually assigned networks. If you can't afford a network engineer or a machine learning expert, then I don't think you can afford the cloud time of 61 GPU years, especially in 2017, where they're a bit more expensive. But in later experiments, they used several techniques, such as a micro search space, which we'll talk about in a few slides' time, and reduced it to 5 GPU years, which is still too much for me, but many more modern NAS techniques have now only use a single GPU for less than a day, and as we'll talk later, some are even quicker than that. So before we can talk about what a micro search space is, this is a very key technique which is used to reduce the training time of a neural architecture search. We need to talk about what CNN blocks are, because this is where the idea comes from. So if we look again at what GoogleNet, you can see that it's made up of multiple inception blocks, which I have highlighted here using those brackets. And if you look in the bottom right, you can see that that is basically the inception block, which has made up the majority of their network. Many off-the-shelf CNNs use similar structures, such as ResNet with their residual blocks. Effectively, they find an optimal structure, and then they repeat it again and again, and use that to train the network. And so the micro search space is very similar in concept, as instead of searching for a whole network, we instead search for what we call a convolutional cell. And this massively reduces the search space, as these are then chained together. So instead of having a search through an effectively infinite search space, as you can always go deeper, you can always add another layer, you can always change layer, we now have a very small defined structure, And for example, this cell I believe is off darts. There's a different, if we look at, there's a different, very similarly shaped cell, which I think we'll look at later from the NASBench 201 search space, which only has about 16,000 architectures, or maybe closer to 15,000, which is a lot smaller than an infinite number of them and makes the training time a lot better. In earlier, another very key time-saving technique was called weight sharing. So weight sharing is a tool which, again, we use to reduce the training time. And the idea is that similar architectures can share weights across a search space. So, for example, if you have these two cells, which I've copied, which this is roughly the same shape as the NASBench 201 cells. If you imagine each color is a different sort of operation between the four nodes, these two cells are quite next to each other, differing only by a single edge. The question that weight sharing asks is, if I point to the green operation, it can be any of the operations that are the same color, can we share weights across these cells? And if we say yes and accept that, we can massively reduce the training time, as instead of having to train 15,000 cells, we actually only need to train about 30 edges before we can just start copying the weights over. So this is a few problems that come from the original versions of all the early NAS methods. Most of these were found by a single paper called Evaluating the Search Phase by Yu et al. And one of them that they found is probably not surprisingly here because it is in computing, is seeds and reproducibility. Many early NAS methods neglected to mention the seeds used in their experiments, and this prevents the results being reproducible or verifiable. This goes even further in some cases where the code is broken or you don't know the code is missing, and dependencies lists are sometimes not given, or the files don't exist anymore. When I've tried to reproduce certain works and I've gone looking, I'll sometimes have to go through the GitHub issues to find what the dependencies are, or find a dependency which doesn't exist anymore unless you're on Mac for some reason. This problem, however, isn't NAS specific. It's everywhere in computing. And luckily, more modern NAS works tend to give the seeds of what of their experiments. Dependency lists are a lot more common, so we are going in the right direction. But as always, it's important, I believe, to strive for more reproducible works. Another issue that the paper found was restricted search spaces. So we talked about search spaces, how they can affect the training time, because we've used weight sharing to massively reduce how many spaces you actually go through. But they also affect the results you can get. And it was found that many of the early NAS methods had two constrained search spaces. And this basically meant that most of the architectures were good. They would produce good results, which meant a randomly sampled network often gave competitive performance as a search for network. And so many of the search methods didn't significantly outperform random sampling. And in the case of NAO, if I remember correctly, or neural architecture optimization, random sampling actually outperformed that search method. And this also ties in with the unevaluated search phase, where many algorithms would present their results and state they were because of their search method. However, they often also presented a new search space in the same paper. So it wouldn't just be, oh, this is our search method using differentiable architecture, differentiable equations, but they would also include, oh, this is our new search space. And both these factors affect your result. If the architectures in the search space are good, you're going to find good architectures. If all of them are bad, they're going to find bad ones. And so we can't really say if the results are because of the search method or because of the search space themselves without ablation studies. And it also meant that methods weren't directly comparable. Sure, your method might get at 6% more, but if my search space doesn't allow you to get that 6% more, that doesn't necessarily mean that your search method is better than mine. So luckily at both these problems, NAS benchmarks are a lot more common now. NASBench 201 is a popular search space which contains both good and bad networks. As you can see from these graphs here, the bottom one is a version of ENAS's search space. And although it's the validation accuracy, you can see that most of the architectures give above 80% accuracy, while in the NASBench 201 search space, it's a lot more varied from about just under 50%. So there's obviously some bad networks in that search space. And since they use this search space, since a lot of networks at least will use that if conjunction with another search space in ablation studies, we can now directly compare. If you're producing one result on your method and I'm producing a different result on my method, we can actually also look at the true optimum, see how far away we are from it, and we can also see where each of our methods rank in comparison. So we actually know how many architectures are better than mine yours would find. The final main point that Yu et al. Found in their paper, which was a problem, is with weight sharing itself. As a quick reminder, so weight sharing, as I said, is a technique which we use to speed up NAS, and this involves similar networks using sharing weights across similar edges to reduce the amount of time training. The problem with this is they found that algorithms that used weight sharing produced architectures or ranked them as the best, and the true ranking didn't correlate at all. So I find this graph a bit confusing, but it's from the paper. But essentially, effectively, the right-hand column, the numbers indicate the disparity. So if you can see, the architecture which would be ranked 1 with the ground truth was actually ranked 8 and had 7 positions of disparity. And we have some networks which have 17 positions of disparity, 14. It just doesn't correlate. So it's kind of hard. It just doesn't correlate. So we found that weight sharing actually had a negative effect on it. And in fact, they found that the more weight sharing you had, the more disparity there was. And this is because small differences still require different weights. It is a very helpful idea to reduce time, but it does affect the actual results. But despite its problems, it's still a massive time improvement. So I have seen some methods that still use it. We don't necessarily need the best architecture in every case. We can need a good architecture. As long as it still find a good one, it's still a usable method. Some methods try to mitigate its effects using other techniques. There's a NAS algorithm called FastNAS, which weight shares only in blocks, so it doesn't weight share across the whole network, which is to mitigate the effect. As we saw in the paper, the disparity generated by weight sharing is correlated to the amount of weight sharing itself. And there are methods that avoid weight sharing altogether and use other techniques, but they each have their pros and cons. So now I want to talk about 2 concepts that might come up later in with people's presentations. So I just want to make sure that we understand that. And the first one is one-shot NAS. And basically this means that it means neural architect search, and we do everything in one training run. So if we have this mini network where we've got 3 nodes and 2 edges between them, and we don't know which operation to use, in traditional machine learning or in traditional NAS, you would say, okay, well, we're going to have the first layer be a 1x1 convolution, and then we're going to have a 3x3 convolution for the second edge, and we're going to train that, then we'll train the next one. And so in this case, you'd do 9 total training runs. Instead, in one-shot NAS, you'd create a supernet where you mix all the operations together and train them all in the same run, which usually takes longer than a single run, but is often quicker than running all 9. And then afterwards, you just deactivate the edges that you don't want, enable the ones that you do, and you do that 9 times and just evaluate it, which is a lot quicker than training. And then you do fully train the best one out of the 9 that you get. And next, so another concept is very similar. One-shot NAS is zero-shot NAS, and this effectively means NAS without training. You don't run a training loop, or at least not a full one. Instead, proxies are used to estimate the performance of a network without fully training it. Now, this proxy can be generated from some sort of algorithm, which scores the untrained networks. This is the example in the paper called NAS without training, funnily enough. And other methods sometimes perform short runs on mini batches of the data set, only for a couple of epochs, rather than fully training it. Effectively, it's just a way to perform NAS without having to do a full training time, because that is the main cost of NAS. So I've talked about problems in NAS, but I want to now focus on the future and problems for NAS. So these are things that we want to work towards, or that I think NAS would be a very good thing to use. And the first one has been probably surprising. It's the search time versus accuracy. Ever since the original NAS paper, we've tried to make it faster and faster. We want NAS to be as fast as possible, but we do need it to be accurate. And this tends to be a trade-off. The higher accuracy we want of being the best network, the slower it takes to actually train it. If NAS is to remove the need of manually designed networks, as the original paper suggested it could, or off-the-shelf networks, we need to be able to generate networks from NAS quickly. Because even if we have methods which take a day, for many problems, I can just download ResNet and retrain it within an hour. We talked about the micro search space. A problem that some people have identified is the micro versus macro approach. So many NAS methods, as I said, are evaluated using NAS-Bench 201 or other similar search spaces, and these are usually micro search spaces. You search for a convolutional cell, which is chained together rather than a full architecture. And if we agree on a point from earlier that different data sets have different data sets require different networks to find their best performance, then we have to make the assumption that a micro search space is not going to be the best network for every data set. As such, we need efficient methods of exploring full networks, and not only in terms of depth, as I said, you can always add one more layer, but structure. NAS-Bench 201 only looks at cells with 4 nodes and 6 edges. Now, they do use skip connects, which could argue does alter the structure as it has a smaller size, has a smaller cell size, but we want to have a look at bigger networks with weirder topologies. So an interesting one that I found, I heard at a different conference was, if everyone remembers a few years ago, transformers were all the rage. There were many papers that had that were talking about transformers. Transformers were the new big thing. They were designed by humans, or rather, the architecture was found by humans. But if NAS is supposed to be about automating architecture construction, why wasn't it employed to find? Why didn't it find the transformer? NAS currently looks at optimizing specific structures and topologies. As I said, we use a very specific search space for a very specific structure, but there's no reason necessarily that it should be limited to that. If NAS is about automating network design, if we apply a sort of more infinite or less so infinite, but a bigger and more fluid search space, why can't NAS be used to find what the next big architecture will be? Why couldn't NAS find the transformer? Why couldn't NAS find the whatever is going to replace the transformer? Another big problem with NAS is accessibility. Although it's not as big a problem anymore, as usually it just requires a single GPU and a day and some other tools. Not everyone has access to these tools. You don't need to be Google anymore, but if businesses are incorporating AI into their business plan more and more, as we see more and more, smaller businesses which can't are simply going to struggle. NAS removes the cost of an expert, but the question is, can we go further? Can we develop NAS which anyone can use? Can we make NAS that I can generate off a laptop without a GPU, just off the CPU? Can I generate a NAS? Can I use NAS to generate a network on my phone to suit my business needs? And there are definitely works that look into this, and is very interesting area of the research, because it's an opportunity to help small businesses compete with the likes of Google, who have effectively infinite resources. The final problem or challenge I want to talk about NAS for is accuracy overall. So very often NAS is evaluated in terms of test accuracy. You run your NAS algorithm, you get your network, you test it on your data set, and then you say, okay, my NAS algorithm reduced a network of X%. However, the problem is accuracy isn't the most important network metric all the time. In medical settings, precision is often more valuable. You don't want to have any false positives. If you are diagnosing a certain type of disease or condition, you don't want to tell someone they have it when they don't. And in mobile settings, as I said, when talking about making it more accessible, multiply accumulate operations are also important. You want to reduce those as much as possible. A challenge for NAS is to shift away from accuracy being at the forefront and develop algorithms that can match a user's need. And we do see that in some algorithms where they will return a portfolio of different models along a Pareto front or trade-off of different metrics, where you'd have a model which optimizes for accuracy or optimizes for, in this case, in a mobile case, multiply accumulate operations. So that is the introduction to NAS. Thank you for listening. We have got 10 minutes before our keynote, so if anyone does have any questions, feel free to ask. If not, we can move on. Okay. So I'll go back to the page. So just for people on Zoom, I was asked of what does the rank when it was coming out incorrect to this image here. So this was basically in this paper they took 32 architectures from a search space and fully trained them to find what the ground truth of them was in terms of accuracy. So then they could rank them, saying, "Oh, this was the highest. Actually, this was the," and it wasn't necessarily that they were that the NAS algorithms were incorrectly or rather were worse or better. It was just the actual what the NAS algorithm would actually say is the best network would have no correlation to its actual position. So, for example, as I said in this, they found that an architecture which was actually ranked 6, the NAS method was saying, no, this is number 1. The architecture that was number 1, they actually said that was number 8. There wasn't a correlation between what the NAS algorithm placed them and their true placement. No problem. Right. There are no other questions. Then, Radu, are you fine to start a bit earlier? Yeah, so I'd like to introduce Radu Marculescu from the University of Texas at Austin to give his keynote, and we're now going to swap over.
Okay, so I should go in my. Can I get rid of this?
Just, yeah, if you drag it to the top, it should then. And then press that button to turn.
No, not working. No, not working.
Just sharing this screen for you, okay? Click and share. And click and share.
I think that's what you said. I think don't pay attention.
Just press this button all the time on.
Oh, okay. Good. Wait. Not making the sense. Okay, I can have it better than. Oh, I got this one. Okay. All right, try this. Yep. Just want to make sure nothing falls in. Yeah, okay.
Okay, so sorry about the wait there. I think this hopefully we're set up now, and I would like to again introduce Brandon Markulescu from the University of Texas at Austin to give his keynote on zero-shot neural architecture search challenges, solutions, and opportunities.
All right. Thank you. Thank you very much, David, for your nice introduction, and thank you everyone for coming to this session and to show interest in zero-shot NAS. So just to start a little bit from the title, luckily we had this introduction. So the neural architecture search is essentially about solving a optimization problem where we have a search space, typically a very large search space. We have constraints that the most well-known is the accuracy, but we also can have other constraints like latency. It's too far. Yeah, accuracy, but also power and latency. And the idea is to find the best solution that fits into a certain computational budget. That's the idea. Why was NAS such an interesting topic to both industry and academia? Was because it promised to move from this kind of manual or ad hoc design, like was shown in that GoogleNet example, to systematic solutions that can lead to optimal designs that can be used for different applications. Now, the zero-shot NAS in particular promises to get rid of the training altogether, so therefore to improve significantly the time for finding these solutions. So it's a hot topic within NAS, so to speak. And the basic ideas at the end of the day is to use some sort of proxy or some sort of metric that can capture very well the behavior of the network and the performance metric that you're trying to optimize, let's say accuracy. And in this talk, I'm going to go comprehensively over various classes of such proxies and see how they can be used to design better architectures, better networks, and what are the limitations as well as the promising directions for future research. So, okay. As I suspect that there is a broad range of expertise in this room when it comes to zero-shot NAS, what I'm going to do, I'm going to structure this talk in three main parts. So the first one is essentially meant to answer the why question. Why zero-shot NAS is important? Why do we care about it? And hopefully motivate many of you, if not most of you, or all of you, to do research in this area. Then I'm going to get into the how. In other words, what approaches or what methods can be used and what do they mean, particularly for zero-shot NAS. So this is the proxy part. Third, I'm going to answer the what question. So in other words, what can we get? What kind of results can we obtain? And I'm going to go into many results that, or many evaluations that will show a broad range of solutions and a broad range of applications that can benefit from it. And finally, closing back to the why, in other words, what can we do to improve, to mitigate the limitations that I'm going to mention and get better solutions or better results for the future. Okay. All right. So now to set up the scene, given my particular expertise in this area, I'm going to talk about NAS in the context of edge AI. In other words, edge intelligence, where the idea is to make all these ubiquitous devices intelligent, typical for applications like Internet of Things. And in this context, the classical solution, when we take the models from the cloud and we just deploy them on devices, has some limitations. In other words, we have to deal with issues related to the communication issues, to the connectivity issues. The connection may not always work. We may want to keep the privacy of different models for different users. So there is a lot of stuff going on, particularly given the wide class of devices that we can have in this situation, ranging from your phones to your Fitbit to other such devices, some of them being even medical wearables that have very private information about our health. So in this context, taking the models as they are from the cloud, it might be problematic because typically these models are big and don't fit easily into this kind of devices. In this kind of devices, we have limitations when it comes to computational processing. We have limitations coming from the memory space that we can use to save these models. We have limitations when it comes to the battery level that we can afford to use with these devices. All of them are limited by the amount of battery that we can use before getting back to charging them again. So in this case, the idea that one can develop NAS approaches that considers the hardware limitations, we can call this hardware-aware NAS, is very appealing. Okay, and in this kind of situation, the fundamental research question that one can ask is how to design these efficient networks that can be used to run this kind of applications directly on edge devices. And when I mean applications, I mean anything from home and smart home, automotive, autonomous driving, mobile wearables, things of that nature. So there is a broad range of applications that can benefit from such a solution. So just to get a little bit into the basics, there are many approaches that can be used for hardware-aware NAS. I'm going to only skim over the important concepts here and get to the heart of the matter, which is the zero-shot NAS. So in general, we start in this problem space with a target device. A target device meaning anything that can be used to run this application, which could be a very powerful phone, could be a FPGA, could be a microcontroller. So it's a wide variety of devices. And in this case, we characterize these devices and we have some sort of idea about their performance metrics. Then we have the search space, which is a broad, a very vast space where various architectures can belong to. And then we define what we call a search algorithm. So an algorithm that will go systematically over all these possibilities and choose hopefully the best one that will fit our application. So in general, there are three categories of approaches that have been developed. So the multi-shot methods that were mentioned earlier as being based primarily on reinforcement learning or some sort of evolutionary algorithm. Then there is the one-shot learning, which was again mentioned as being more efficient than the multi-shot. And finally, the focus of my talk, which is the zero-shot approaches, which are the most promising approaches among all, because they promise to get away with this important step, which is very time consuming, and it's the training step. So just to go once over lightly, the multi-shot approaches will have typically some sort of controller. So we call this a NAS controller that generates a description of the circuit. The description is converted into an actual circuit having real operations as shown here. This one is trained and some performance metric is extracted and it's fed back into the controller over multiple steps such that we get in the end what we want. So through successive refinement, the architecture becomes better and better, and hopefully we get a reasonable solution in the end. The problem with this is that it needs a lot of time, okay? And therefore, it's kind of limited in terms of applicability to anything but small examples. One-shot NAS, okay, it's a significant evolution over multi-shot NAS, because in this case, we simply build a hyper network, which consists, as shown here, into nodes that are feature maps and to edges that are different types of operations. And basically, we train only this hyper network. And during this training, we kind of emphasize the important operations. And in this representation, the important operations are shown with thicker lines, okay? So then in the final stage, which is essentially the one that generates the architecture, we basically get only, go ahead only with the thick ones. And therefore, these are the most important ones that will, by important, it means they affect the most the performance of the network. And in this case is a significant improvement compared to previous approach. Since was mentioned, I want to bring again the weight sharing approach that can even bring even more improvements over this one-shot learning. But at the end of the day, the fundamental step, which is the training step, remains there, hence the desire to develop time efficient and hardware-aware approaches that will eliminate this step altogether. So my last bit in terms of motivating the interest for these zero-shot approaches comes from a sustainability angle here. So we talked about getting time efficiency, getting various things, but if we think in terms of this search, the cost of search in terms of CO2 that is consumed, and this could be a serious problem in the long run, and the accuracy that we get, you see here different levels of accuracy and different classes of approaches. The ones shown in blue here are the multi-shot ones, which are obviously the most expensive ones. The orange ones here are the ones that belong to the one-shot approach, and you see many circles. That means many versions of this one-shot approaches have been proposed. Some of them having more or less computational requirements. You see here the computational in terms of MAC operations, multiply, accumulate. The smaller ones take less, the bigger ones take more. But you also see the promise of the green ones, which are far less dense compared to the others. But in this case, you see, for instance, an approach like this gives a very high level of accuracy, yet at a fraction of the cost compared to one of the approaches here or here. Let alone these ones, which have a lot less. So this is another way to think about the importance of having such approaches that can provide us a good solution without having a big impact on sustainability. Now, there is another angle to this problem, and hopefully I'm going to convince you by the end of my talk that this is an important one. Despite all these things, all these improvements that we can get through zero-shot NAS, there is one more angle, which is this having these approaches developed can deepen our understanding, our theoretical understanding of why certain architectures work or give better results than others. Okay, and this is an important thing as long as we think of having the next generation of classes of, I don't know, super transformers or whatever that will do things very efficiently. So this is another thing to keep in mind. So I hope that by now I convinced you why it's important to get these zero-shot proxies. And now I want to get into the how part, so to speak, what are the methods, what are the approaches that we can use. But I'll start by mentioning two proxies that probably most of you, if not all of you, have used or have seen in any kind of problems of this nature. And these are specifically the number of parameters, okay, and the number of flops. So people have used and still use number of parameters to compare different architectures. So they said, oh, this one has fewer parameters, and you see this reported everywhere. Oh, 1 billion or whatever, or this is 100 million or whatever, or this is few millions parameters. It's better than this because obviously it can fit smaller devices, right? So this is still very much of use. I don't brag about it a lot, but I'll keep constantly in the presentation. And the second one is the number of flops. Typically, the number of flops relates to the complexity, the computational complexity involved. So this is also very important. And I want to make this clear from the very beginning, because in many of my comparisons shown later, you will see this brought up constantly, the number of parameters and the number of flops. And actually, a little bit counterintuitively, they are extremely good and extremely competitive with this kind of quite refined or quite complex proxies that are based on gradient accuracy proxies or gradient-free accuracy proxies. So the big picture means that a good network can be designed when all these three criteria shown here in these three bubbles are satisfied. And by these three, I mean the capacity of expressiveness. So basically, the model that we have, the proxy that we use to design that should be able to capture subtle patterns that correlate the network behavior with the objective at hand, with the application at hand. Then should have a good generalization capability. In other words, should be whatever we do and we derive with known data should work well with unseen or out of distribution data. And finally, it should be trainable and converge pretty fast to the result that we want, because that shows a very competitive result. So all these things somehow together can bring a very good solution, a very good network. And it's important to keep this in mind as I'll go to the details of this, because this impacts actually the quality quite a bit. So let me start with one of the simplest proxy, so the gradient norm. The gradient norm is pretty basic. So basically measures the sum of the L2 norms of the gradients across each layer's parameters. So here is a formula that shows you have here the gradients of the parameters. Theta I are the parameters. I here is the layer. Okay, so you have layer from 1 to D, where D is the depth of the network, and you have the loss function shown here, and is a norm 2, so the square. Basically, this is what is a mathematical formula that can be used to understand the propagation, the gradient propagation through the network, given all these layers that made up the network. So the idea is that by knowing this, or by using this during the design process, we can have a good idea on the behavior and how that will behave in terms of, will impact the quality of the metric that we're interested in, let's say the accuracy for the sake of simplicity. The problem with this is that it captures the gradient propagation properly, but does not consider the parameter importance during inference. And this brings me to the second one. So I'm going to build on this, in terms of sophistication, starting from the very basic to the most sophisticated one a few slides later. And each and every time I'm going to add something new in terms of complexity or sophistication in terms of that specific proxy. So this one, SNP, single shot network pruning, is the one that brings the importance into the picture. So to jointly measure the parameter importance for both forward inference and backward gradient propagation, this considers a more sophisticated formula. This is called saliency, which tells a lot. And in this case, it's basically the product between the
do you agree? Do you think like for video generation there will be a trend like model like pre-training, supervised tuning, RLHF, and all those kind of complicated, more like engineer instead of research kind of process.
I don't know, is this for me?
No,
The other room audio.
that is weird.
Oh, okay. So clearly or I cannot cover them because they do the mind. So I can keep going.
Yeah, keep going. If that was again, I'll go to the other room and ask.
Okay. The question is which one? Okay. Yeah. So I was saying in this case, this is the saliency, which essentially looks at the product between the parameter magnitude itself. You see that I here, the gradient, and
Next presentation. we have,
very cool.
this question,
Is this because of Zoom, right? It comes anyway, right?
Like directions, shadows, these kind of stuff in the generated models, because
The funny thing is that it comes loud and clear, right? So it's not we can listen to that.
photorealistic conditions, the generation process. Thank you.
So in this case, I was saying that this saliency gives a sense of importance of the parameters. So what it means, it shows that some parameters are more important than others. And therefore, if we think about the importance of those, we can maintain those and eliminate the ones that have a lower importance, lower saliency score, such that we can prune them and therefore focus the training only on the important ones. So the training still remains part of the picture, but with fewer parameters, therefore the efficiency increases over the previous one. And hence this is a significant step compared to the previous proxy that I showed. So in this case, in case you wonder, this one, the brackets here show here, this is the inner product sign that I used for this representation. So compared to the gradient norm, this is a step forward. So this is supposed to give good results. And of course, it has the limitations as to what exactly, how exactly the effectiveness of this relies on the assumption that the initial gradient importance of weights correlates with the actual network behavior. The important thing for you to understand from this presentation at this point is these are mathematical constructs that can be used to give some importance of some weights versus another. And therefore, once you set a threshold and you say, okay, this is the threshold that matters to me, you can eliminate the others and train with this. So basically the training goes with a simplified circuit because the number of parameters is fewer. And therefore, the approach is faster and hopefully leads to the best results. But there are still things. How do you decide that threshold? How well the proxy itself correlates to the actual behavior of the network? So there is no silver bullet, but there is progress as we get in terms of sophistication and hopefully best results in the end. Now, okay, now I'm going to move to one that is even more complicated. So this is the Jacobian covariant or Jacobian covariance, in which we do a lot more compared to the previous one. So basically, this addresses the issue over the input data to reflect the network expressivity. So for instance, if you look at this formula shown here, J is the Jacobian, it's basically a matrix that contains all these gradients of the output Y for a particular batch B with inputs X1, X2, XB, which is the collects all the gradients with respect to all the inputs. So why is this great? It's great because it gives you a sense of the sensitivity of the output with respect to the inputs. So this is why it's interesting and whatever. So the way you build this is essentially by building this covariance matrix, doing this, collecting all these gradient calculations, finding a normalized version of it, then computing the eigenvalues, And then these eigenvalues are used to compute this proxy, the Jacobian covariance or covariant, which has this lambda as the eigenvalues and some small value added here for numerical stability. So in general, there are many subtle aspects here from a mathematical standpoint of view, but what's important for us here is that this reflects the network expressivity. Remember those three bubbles that I showed earlier, and in general is a complicated approach in terms of computational resources that's needed, because we move from scalar that I just talked earlier to matrix type of information processes, which is this Jacobian. Okay. One more level. So this is an approach called ZICO, which we proposed at iClear last year. And this one is even more sophisticated, but is a significant change as it introduces a new type of metric that combines the mean, you see here the mean, and the standard variation of the gradients across batches to evaluate the network architecture. So the formula that is computed here is based on what we call the inverse coefficient variation, okay, of these gradients, which serves as a metric to assess the potential performance of different architectures. So what is this? Is essentially the ratio between, is essentially the ratio of the mean to the standard deviation of the gradients. And in general, high ICV or inverse coefficient variation values indicate stable and significant gradients, therefore more important coefficients. So this is what is used. So the intuition behind this is that the parameters with stable and large gradients are likely to be more important for the network or the architecture of the network to obtain high performance results. So in other words, these are the ones that should be considered during training and basically get rid of the rest. So it's again, it looks into the importance to finding the importance of certain parameters compared to others in order to do this. Just to clarify this, it doesn't involve any training. This batch that you see here is just the initialization one that is used to do these derivations. And after you eliminate the parameters that you don't need and you keep the ones that matter the most, you can do just regular training, which will be far more efficient. It does have, so it's easy to implement, but it does have an overhead because essentially of this calculation. So these gradients should be calculated twice, once for the denominator and one for the variance at the denominator. And the problem is that they cannot be computed in one single step. So you do two steps to compute them, because otherwise it will be a Jacobian, right? If you do it at once as a matrix. But overall, it's a interesting approach. It's an interesting twist, and you'll see in the evaluation part, it gives quite consistent results. So the question is, everything I presented in the last few slides were having this approach, these proxies that are based on gradient calculations. Let's see now, what can we do about the gradient-free calculations? Okay, how will this work? And here I have a couple of approaches that I want to mention. There are others that can be mentioned. I'm not exhaustive in this presentation, but I just highlight the ones that have a significant shift in terms of intellectual sophistication compared to the general trend. So one of these is based on the number of linear regions. Okay, so the basic idea in this case is that the linear regions correspond to unique activation patterns of the neurons in the network. So for instance, if you think about this multi-layer perceptron, and you have this input and you have this output, all of them, assuming the binary case, when everything is simple, shown with 0 non-activated, 1 being activated, the input space can be partitioned, and for each activation, as you see here, a certain region corresponds to a linear behavior of the network That's the basic idea. So once you get this type of thing for the input, then you can create some codes, as you see here. So that you associate codes to different regions. And in the end, by putting all this together and you get a matrix here, the more this matrix resembles to a diagonal matrix, the better for the performance of the network. In this case, the formula that we use, or the proxy that is used, is shown in this formula, where you have the number of linear regions here, and you have this the matrix type of representation, where DH is the Hamming distance, and these are the codes that correspond to these different representations. And the basic idea is that the smaller the Hamming distance between two different codes, the harder will be for those networks to differentiate between those two types of behaviors. So once you have this log that type of formulation, you can get an idea on what matters and what doesn't matter. Again, is the same idea, that has to be used. And the basic idea is that the larger the value, the better the behavior of the network. Of course, there is the issue of the exponential growth of these linear regions, particularly for complex or deep networks, because that the problem can clearly increase in complexity very fast. But nevertheless, the results that have been obtained and the results that have been proposed are quite interesting, and you will see later in the experimental results. Another class of approaches, so in this case, we saw a change from the mathematical formulation in the sense that is not just gradient, but also involves something like the topological concept of the linear region, as well as the coding through those codes associated, as well as the Hamming distance. In this case, we go in a different direction. We still increase the sophistication. And in this case, we bring together the concepts in the relationship between the gradient behavior and the gradient properties and the network behavior on one hand, with network science on the other hand, and particularly small world networks. For those of you who are not familiar with the small world networks, those are the class of networks where distant nodes may look very close, in fact, in terms of behavior, due to the long range links that connect them. Okay, so for instance, typically in epidemics, the effects are a lot worse than would be in a grid-like structure if all of us will be in a grid, because precisely we have this long-range links, and therefore the small world effect comes into the picture. In this case, we can look at the regular. You see, you have a network that is wide and deep. You see the values here. And you can see that we can identify two types of connections. So we can identify cell-to-cell connection. This is a cell. So we have these networks that are called short-range links, shown with black. But you also have these long-range links that skip multiple levels, shown with this purple or this red, that create this kind of small world effects. So in other words, in this case, we take a topological or a structural view on the network, and we try to see if we can identify any proxy or any metric that will reflect that in terms of quality of the network, in terms of achieving a higher level of accuracy. And in this case, we define two metrics. One of them is so-called density of a block, which is the ratio between the number of shortcut links in the block and the total possible of shortcut links in that block. And this is the rho B, the density. And then the most important one, which is the NN mass, shown in this formula, which incorporates this rho B, you see it here, which essentially gives us the idea of the mass of the network. So the analogy here is that in physics, if you think about density is a mass over a volume, unit of volume, right? And the idea in this is to associate to the neural networks a certain mass, which is density, and you can think this as an equivalent of a volume, which comes from the product of width and this. So we don't look precisely at the topology like an adjacency matrix, but we look at this through the statistical properties that are important to this density and to this NN mass. So this is the fundamental change in the understanding. And the idea is that the networks that have higher NN mass are better from quality. So what it means is that similar to, I'm just giving a everyday example. If you go to a market and you see, okay, this watermelon is heavier than this, well, this may be better for me because I want more to eat. The same thing. So if this has an NN mass that is higher than this will give me a better result. So I can say that a priori before training or doing anything with that network. So this is the advantage of this, and this is why this is a zero-shot type of approach. Last but not least is the variation of this. It's called NN degree, which relaxes a little bit the width requirement that I mentioned earlier. And in this case, the view is similar but slightly different. So what do we do here? We do two things. First, we look at any regular network shown here, okay, as an overlap. That's why we say this network equals this plus this. So essentially this is the real network, which is an overlap between a regular network and an irregular one that has only this long-range link. So essentially is an overlap between a lattice type of network and a random type of network that is based on these long-range links, okay? And this is the idea. So again, we look at the structural properties of the network, but through a statistical lens that gives us this kind of metrics. I'm not going to get into the details. There are many mathematical details and theorems, proofs that are interesting to understand this kind of approach. But the final result, which is kind of deceptively simple somehow, shows that we can do the NN mass, the NN degree, I'm sorry, of this cell as the sum between this, and then the NN degree of a given network is just the sum over all the cells. So a cell is the one that has the same width and a certain depth, okay? And when you sum all these, you can get a G, an NN degree of the network that is here. So the greatest thing about this is that is extremely simple. It needs only 3 parameters. So essentially it has WC, the width, the total number of skip links, and the DC, which is the depth. So these are things that can be observed at sort of macro scale, and you can get an idea of a network, how good or how bad it is. So the interesting thing also from a slightly different perspective here is to acknowledge that this type of approaches look at macro scale properties of the network, although they characterize the structure at the fine scale somehow. So the very fabric of the network comes into the picture. And it's interesting because this kind of approaches, again, enable to do good results, to obtain good results with very few parameters. You may ask me, why do we need this? Why were the previous ones not enough? Okay. Well, it's interesting that these kind of networks are relying on these statistics to get properties for specialized architectures. So these were shown results to help for the DenseNet class of networks, ResNet type of networks, as well as MobileNet class of networks. What's common among all of them? All of them have this kind of long-range links. So it's a property that can be exploited for particular class of architectures, but motivationally speaking, why is this important? Because the previous ones, although they are the same, if even not more sophisticated, as you'll see shortly, they don't necessarily perform better than number of parameters and number of flops. So why is this angle needed is because you cannot see one size fits all type of metric. And these one are metrics that are trying to be specialized a little bit to certain classes of architectures in the hope that they will give better results compared to the general ones. In other words, the ones that are purely mathematically justified. Okay, and we'll see this in a short while. To summarize, okay, these are approaches that I mentioned in terms of proxy, norm, SNP. Didn't mention a lot of them, then Jacobian covariant, then Zico, and then from the second category, I mentioned only log depth, NN mass, and NN degree. So with respect to the three qualities that I mentioned earlier, meaning the three bubbles that I mentioned that will make a great proxy, you could make 3 or 4 observations here. The first one, probably the most obvious, is that this class is significantly imbalanced compared to this one. So you have a lot more in this category compared to this category. So the gradient approaches dominate. Obviously, the gradient approaches are more complex, as I said, simply because you need to compute gradients as opposed to the gradient free, which you don't. So the efficiency of this, just from the get-go, will be significantly more compared to this. So one possible direction will be to focus to develop on this one and develop better approaches for this. Another observation, even in this class alone, you can see that the vast majority of the approaches focus on trainability. Very few focus on expressivity or generalization capability. So the ability to work with unseen data or out of distribution data, just 2. All of others are doomed to fail from the get-go. Last but not least, if you look at this class, gradient free, the vast majority follows on expressivity. None of them focus on generalization capability. And last but not least, there is not a single approach that covers all 3 of them. So this shows you, in principle, fundamental limitations of all the proxies that have been published to date in dealing with any general case. Why? Because they either good here, or good here and here, or good here alone, or good here and here. So in principle, it's like you need 3 points to determine a plane, and you have only 2 at most. In most cases, 1. So this probably should be as a general guideline as to what should follow next in terms of good proxies. So I'm going to go to this last step of my presentation. So essentially evaluation. David covered some of the benchmarks. That makes my life a lot easier. So I'm going to focus just on the second part. The benchmarks are specifically benchmarks developed for NAS evaluations. In other words, they are providing you certain data sets like CIFAR 10, 100, or whatever, but also certain model architectures to deal with. And probably some of the most known one is like NAS Bench 101, 201, so on and so forth. So as mentioned earlier, what's great or what's interesting about it, each of them is built by stacking multiple such cells. Each cell will have six operations. You see the edges. Again, I'm talking about the NAS Bench 201 here, and 5 candidate operations shown with different colors. And the NAS Bench 101 have the same structure, just more examples. The interesting part, to me at least, is the hardware-aware cases when you have, in addition to these operations and this kind of things that we discussed, we have also results that have been provided specifically for different target architectures, for GPUs, for microcontrollers, for whatever. And in this case, typically, we're talking about latency or energy figures. And you may wonder, what do you do with it? How do you connect? And I'm going to show you just one connection, which takes the very last one that I mentioned, meaning the NN degree, which look like nothing probably you have seen before, but yet can be used in a very concrete framework that consists of 2 steps, one in red, which is about building hardware performance models for a given architecture. And then the second blue box, the bigger one, which shows how this can be used to get the optimal architecture. So we have performance metrics here. We have a general search space here. And then basically you can do these proxies, you can do these estimations, and you iterate multiple times, such that at the end, this very D-star architecture that you get is the optimal one. What means optimal one? Highest accuracy, yet satisfying the energy budget or the latency budget that was given to it. And this is new. And I'm going to show you, hopefully this will work, a short video.
parameter to define the direct potential we want to profile. And the third, we use the GetLens function to calculate the net field with the network first. Also, we use the real power function to read the power consumption of one power. After that, we use the profile the hardware performance to transform and analyze to hardware performance model. Now let's take a look at our code run directly on the and compare the speed of one direct or NH0, which was the left window, and the original one L0, which was the right. Now the also, the search cost is much less than the regional algorithm. And finally, our model quality is better than the one level search. To conclude, our non-frequent on the wrong directly on the SUI. So our best knowledge is to source the work to run directly on the typical SUI.
Okay, so you may wonder why did I show this? You see all these parameters, DC, TC that I mentioned earlier. And this comparison is very detailed unless you know the paper. The only reason I showed you this is because of this time. 3 seconds on Raspberry Pi to do a full NAS run. You may say, where is this useful? Where do I care about 3 seconds, whatever? Well, just imagine you send something on Moon or more recently on Mars, if these people want, and something goes wrong and you need to resynthesize something and to be able to run the application there where you cannot go and replace it yourself or use websites to upload a model or whatever. So this will be able to run a new model, find a new model, deploy it, and run on it in 3 seconds on a Raspberry Pi. 3, not even 4. Okay, this is so this shows that as sophisticated and as alien those concepts were with small ones and whatever, they can lead to very complete results where we have actually number measured in terms of energy efficiency, cost of the search, and so on and so forth. Okay, so coming back to the more general evaluations, I want to show a few of them that are based on 2 metrics. Spearman and Kendall. Spearman SPR here, the raw parameters, and Kendall's tau for both. All case when all the networks in the benchmark are considered, or top 5% when we look at the top 5 solutions. David mentioned this earlier. So you see, this is a comprehensive evaluation of CIFAR 10 for NAS Bench 201, or you can see the correlation. In general, these are between -1 and 1. Tau is typically more robust, but 1 is best correlation, -1 is the worst. So you can see if we look at this orange and green, meaning these two for all the architectures, clearly these points dominate. So which one? GradSign, Zico, and the number of parameters. So basically, the number of parameters, that is such a naive approach used by everyone, performs very well, and in fact, a lot better than far more complicated things like Fisher, Jacobian covariant, and whatever. So this shows that this effort should be realigned with this kind of evaluations, so to see which ones to use, okay? If you look at the red and the blue one, which are the top 5% architectures, you see that the ZenScore, the one shown here in red, performs the best. So others perform a lot worse, like you see over here. So first of all, there is no claim that can cover everything, depending on what you're looking for. And also, many of them, either gradient-based or non-gradient-based ones, perform better or worse in different cases. So in this particular case, as I said, these are the 2 conclusions that cover this wide range. This was again for CIFAR 100 data set, but similar results have been obtained for other benchmark sets. Another comparison here involves ImageNet okay, for NATS benchmark. And in this case, you could see that again, all orange and green, these are the best, meaning the highest value, 0.6 and 0.8. And this one here, so again, number of parameters, Zico and Zen score perform the best. If you look for top 5%, these one probably, yeah, these are the best. So you see again, similar conclusions. So a number of parameters in Zico also perform much better than other proxy for 5%. So this is sort of the first longitudinal type of evaluation that we done, and we could see where different of these proxies, therefore different approaches, stand when compared against this NAS benchmarks. Now, everything I talked about here is for CNNs and for this type of regular architectures. In terms of here, we evaluated over 100 VITs, you see. And if you look at these results without too much attention even, you could see that these two are the winners. So in other words, the number of parameters and the number of flops perform better than all these indicators for the image data set as shown here. So these are pretty, interesting results, because it's hard to say that the simplest ones in the end do better or best sometimes for vision transformers, right? So there are many explanations that can be found behind it. Probably one of them being the fact that none of these proxies cover all three characteristics. Some of them have limitations because of the underlying assumptions. Anyway, the result here is interesting and tells an interesting story, I think. Last but not least, we have these results on two hardware. So the first one were unconstrained. This one is constrained with hardware parameters. So this one is an edge GPU that we used. We used a Jetson Nano TX2. And you see in these results, so you have the test accuracy on the Y and different approaches. So this is the Jacobian covariance, this is the SimFlow, number of parameters, so on and so forth. And the interesting thing is to see if we set a certain limit. So we make a problem very constrained. We put a very tight constraint on energy, okay, say 10 millijoules here. So you see in this case, this is the only one that fails. You see, this is the ground truth and none of the data points here. You see gazillions of them in the gray area here. None of them gets even close in terms of quality compared to the ground truth. All others perform decent, see over here, over here, over here. But if you relax a little bit the energy constraint, you move it to 20, it's only 3 approaches that are able to satisfy the constraints, meaning to get the blue points as close as possible to the red limit. And these are, again, the number of flops, the number of parameters, and Zico. So this is interesting. So if you have a problem with a real constraint, no matter what point you will get, you will be somewhere in the gray area. Only these 3 will be able to satisfy that constraint. Last but not least, on a different GPU, so different figures altogether, GTX 1080, you see the story is pretty similar. So we, in this case, it's for latency. If the limit is around 50 milliseconds, only these are very close to the Pareto optimal, only this and only this. So again, this Zico approach seems to be generally the best for this kind of hardware-oriented NAS. If we think about the future, what do you think in terms of applicability of NAS approaches to these kind of things? I think a very general direction that will cover a lot of research potentially is this Gen AI type of optimization. So in this case, the automated architecture optimization is a big asset. So it can help identify optimal architectures for generative models such as GANs or VAEs or transformers. And the process can lead to better architectures. Improved performance, obviously, resource efficiency. And in all these cases, the zero shot can provide a very quick evaluation, and you don't need to spend a lot of time in training in order to find out that your architecture is actually not good enough to get the best results. Efficient fine tuning is another direction. A lot of stuff going on these days follows this paradigm. You have a foundation model or whatever, and then which is fully trained and very well verified, and then you only fine tune it as needed. Again, we can benefit from using this zero shot process to see the importance of different parameters in this case. And only the fine tuning that is done for the parameters that are important are going to matter in terms of quality in the end. There is another one, data quality, that can be used in conjunction with these approaches to determine which one has what kind of impact on the accuracy. But I would like to just take the last couple of slides to reiterate over the important things that are promised to this. So it's the time efficiency, is the interpretability, and is the effectiveness that we can get from these proxies that can and should matter the most. In our results, we have seen, and I think this is a significant mindset change that we have to be aware of, is a difference between the unconstrained NAS when we look at all architectures and the constrained NAS when we look specifically for some hardware constraints, either energy or latency, because in this case, the solutions might be quite different as we see in the preliminary evaluations. And there is obviously the good news is there is a plenty of room for improvement. This can be used to tasks including image classification, object detection, language processing, and many more. So this is great. In fact, if I remember correctly, there are even today some papers that will get into these new applications that will be presented. Last but not least, just acknowledge my contributors. So we have the most direct contributors to this, former students that worked on this problem space. One of them is here. And then for more details on the stuff that I presented, and primarily more results in terms of experiments that we did, are in the TPAMI paper that appeared this April. And this is the title. You can check it out. Thank you.
Thanks. Thank you, Radu. That was a great keynote. And we are a bit over time, but I would like to give people an opportunity to ask Radu any questions. And yeah.
So I'm trying to adopt NAS for video understanding, and I recently
Me too. Me too.
They quite are the best way. However, and in the end, you always end up that you need to compare what you're using, so you need a benchmark, unless you use dark search space and forward methods. But my question would be, what is in your opinion, speaking about generalization, the best metric you have right now to go to improve for video data?
So just before Radu answers that, I'm just going to try and repeat the gist of it for the Zoom. Basically, the question was regarding zero-shot NAS for video use and what's the best benchmark for generalization in that case, if I got that correctly.
Yeah. It's a very good question. Certainly a question that keeps us working on this problem. I don't know a benchmark for this. So the Zico that I mentioned and has a good result for generalization is basically because of this kind of robustness to the parameter variation. But in terms of benchmark to use, I really don't know. And I'll be happy to keep in touch to find, but it's a very good question and problem space to work on. Yeah.
I have another question about, so you discussed several proxies. Have you considered using multiple proxies to create a better predictor of the ground truth performance?
Yes and no, not directly for this type of applications. We try to use for bioimaging, and the results are mixed. And my explanation for that is because we didn't know how to use them. But it's again a very good question. Yeah.
Just because we do have a microphone, then it might be easier for people here. If people do have a question, feel free to go to the microphone.
Oh, it does not seem to be working. Never mind, I'll try and repeat the question then. Sorry.
Okay, my question is about concept of zero shot and gradient based methods. Basically, zero shot means we don't have training. We don't have training, we don't have weights. We don't have weights counted on the gradient.
No, you have weights because you take a mini batch, or you can take a couple of pairs of at the very input. So you assume that is the initialization step. You don't have training per se, the full blown training, but that's how you compute it.
So it limits kind of all this
Yeah, it's just initialization that you use. Yeah.
I need to clarify, but you can correct me if I'm wrong. It's when zero shot is training in the search phase.
Yeah,
So
yeah.
Find the architecture, but you do train at the end, but it's you just don't train while you're searching. So you only train one one network when you finally found it.
So when you train, you know you have a reason to train. You know it's good.
And one more abstract question.
Sure.
Narrow computational search, like if you do it manually, it also involves optimization of hyperparameters like learning rates, weights regularization, etc., like training networks. How NAS works with that? Because sometimes if like all the hyperparameters may impact the results much more than if you just change number of channels.
Yeah, well, we don't have a silver bullet for that, so to speak. So we don't have a approach to say exactly this is the best rate, the learning rate to use for that. So it's essentially an iterative process for that. But again, the NAS per se focuses more on getting the most promising architecture. And after that, the actual result that you get with it, say during inference or whatever, is a separate story because that is part of the training process.
Signal is still hard 76 right now.
Say it again, please. You said what? I could not understand what you said.
The CICO, that one looks like it's normalized grading performs as the size I just presented. And however, this looks like another signal is kind of like a normalized grading, right? Normalized grading.
Is the ratio between the
It's a ratio of the expectation over the
yes
exactly. And in the standardized vanilla, that we can see that a SNP that using the first letter expansion and upper bound just using the grid now. So I'm curious, since it looks that if we can combine SQL with tile expansion, can directly get another SQL. I think that might be another state of art, right? I got curious if this sound work that's already
in comparing Zico with the SNP. Yeah, well, result wise, yeah, we did. And qualitatively, I don't know, probably because this is captures second order effects better, would be another explanation. But result wise, there is no question. It's state of the art. That clarifies. You can probably take it.
Because some coding work ready to some SQL plus expansion. I can give a SQL result. I'm just curious.
Well, for sure SNP has been used for pruning. I'm not aware Zico being used for pruning. I think was just proposed here. Yeah.
In Optimizer, using, for example, using item of W the category. I think in item of item W, the grading calculation is very similar to what the factory still using the normalized grading.
Yeah, we have to probably take it offline.
So because I think as I said we're a bit over time, I'm going to thank Radu once again for a great keynote.
Thank you.
And I'd like to remind everyone that our first session is starting now. It will be until it will finish at 10 to 4. Unfortunately, the first session is in the other building in 4E. I think it's 338
As we are getting, as it is now 10 to, and we are still waiting for people to return from the post session. Since we did run a bit over, we're going to wait a few more minutes and hope that people find their way back and don't get lost. Konstanty, are you in the Zoom?
Hi, yes, I am. Can you hear me?
Yes, can hear you, great. I'm going to stop sharing and then hopefully you'll be able to take over.
Okay, give me a second. Can you see the slides?
Yep, but if you just give me a second, I need to swap the screens around. Okay, so I think that should be fine. So this is our first paper, which is the devil is in the discretionalization discrepancy, robustifying differentiable NAS with single stage searching protocol by Konstanty Sobotko. Take it away.
Okay, just to make sure, can you hear me?
Yep, so can you just
Okay,
run
okay.
away from the mic?
Okay, so hi, my name is Konstanty Sobotko, and today I'm going to present our paper titled "The Devil is in the Discretization Discrepancy, Robustifying Differentiable NAS with Single-Stage Searching Protocol." I'm sorry for such a long title. Yeah. Okay, so in the differentiable NAS, we construct a differentiable search space so that we can optimize it using gradient-based methods such as SGD. And to simplify the terminology, we decompose DNAS framework into 3 stages. The searching stage, where we optimize over this differentiable search space, and we try to find an optimal continuous architecture. Then we have the decoding stage, where we discretize a continuous architecture. And then we have the retraining stage, where we take this discrete architecture and train it from scratch for a longer time. Yeah, and in DNAS, we associate a single scalar parameter with each architectural choice. And if we group them all together, we can form a so-called weight sharing supernet that David has already mentioned. And the supernet contains all possible architecture candidates as its subnetworks. And we want the supernet to be differentiable with respect to both operation weights and architectural parameters. Yeah, and DNAS in general is very efficient, but suffers from a few issues. The issue that we study in this paper is the discretization error. And this occurs when we try to discretize a supernet that has a high entropy of architectural parameters. This issue has been already mentioned and talked about in the literature. And here we show a toy example where we try to discretize a high entropy architecture, and it leads to some errors. Yeah, and ideally, we would like our supernet to have a low entropy architecture so that this procedure does not induce any additional errors. Yeah, so we have a few contributions. So first, we demonstrate and quantify the discretization error. And in particular, we demonstrate its relation and to the entropy of a supernet architecture. And then to eliminate the issue, we introduce a novel single-stage searching protocol. We have some other contributions, but we do not have enough time in this presentation to cover them. So if you're interested, we ask you to check our paper. Okay, so we have a bit unusual approach in a sense that as opposed to other methods, we conduct our experiments in the semantic segmentation task on the Cityscape dataset. And the reason is that our method is suitable only for a particular design of the search space. And so, yes, and we found such a design in the semantic segmentation task, but our approach might not work as well, for example, on the image classification. Yeah. So first, we measure first we measure the entropy of architecture at the beginning and at the end of the searching stage across different methods and tasks. And here we can observe that this entropy does not change much from the beginning to the end of the searching stage, which means that it can cause a discretization error. Yeah, and then we try to quantify the discretization error by measuring performance drop after removing a certain number of least important architectural parameters. And you can think of it as a simple proxy of the discretization error. And we conducted these experiments for supernets trained with different entropy regularizations. And actually, these different curves on both plots correspond to supernets trained with different entropy regularization. Yeah, and in an ideal scenario, if our supernet has zero entropy architecture, then we wouldn't see any performance drop. But in this case, we actually observe a sudden performance drop. And additionally, we also observe that it's correlated with the entropy of the architecture of a supernet. Yeah, so then we considered penalizing high entropy explicitly. So here we did experiments with adding an entropy term to the loss function, and people have already tried penalizing high entropy many times in the literature in this form or another. So we are not the first to do it, of course. But here we, as we saw before, lower entropy architectures suffer less from the discretization error. But here we can actually observe that strong entropy regularization actually leads to worse results in the searching stage. And you can think of it intuitively as harming exploration in the searching stage in favor of having a more discrete architecture. Yeah, so how to get rid of the discretization error completely? Well, our idea is simple. It's to just not discretize anything at all. And so in the standard DNAS framework, we would train a continuous supernet, then we would discretize this continuous architecture to a lightweight discrete architecture, and then we would train this discrete architecture from scratch. Here, we instead we do not discretize a supernet, and instead we just freeze its parameters and fine-tune our operation weights. So here we treat supernet, optimized supernet, as our final model, and we will use this model in the inference. You can think of it also as having a continuous architecture instead of projecting it into the space of discrete architectures. Yeah, so this approach is seemingly naive and overly simple, but in fact, we found that under certain conditions, it can be actually pretty efficient. And namely, for a particular design of the site space, we observed that there's not much difference in terms of floating point operations and number of parameters when you go from a dense continuous supernet to a discrete architecture. So it means that this actually makes usage of supernet in the inference feasible. In this paper, we follow the non-dense variant of the search space introduced by DCNAS, and this search space does not include long-range connections. For those of you who don't know, DCNAS is arguably the most successful application of DNAS to the semantic segmentation task. So of course, our approach has a slightly higher inference cost because we do not discretize anything and we have a dense supernet. But as we will show later, we save a lot of computational resources by fine-tuning weights and not training it from scratch. So as you can see, we also considered a few different variants varying in size of our model. Okay, so now let's look at the results. So here we compare our method to the state-of-the-art DNAS approaches in the semantic segmentation task. First, let's look at the computational efficiency of these methods. For all methods except ours, we provide the number of lobs for their final discrete lightweight architectures. And in our case, we provide the number of lobs of a supernet because we treat supernet as our final architecture. And unfortunately, we do not have an exact number of lobs for the non-dense variant of DCNAS, and we couldn't compute it. But given the set space of DCNAS, it should be roughly the same as the dense variant of DCNAS. Yeah, so here we can actually see that instead of using a dense supernet with the set space introduced by DCNAS, our supernet is still computationally efficient. There are some small differences, but it's not an order of magnitude difference. Yeah, and then we compare the non-dense variant of DCNAS with our medium model. It's a fair comparison because both models were trained on very similar, basically the same set space, but also they have the same parameters. And here we observe that our supernet actually outperforms the final architecture of non-dense variant of DCNAS. And we believe that it shows a potential of our method and that it's capable of achieving competitive results. Unfortunately, we did not have enough time nor compute to conduct more experiments or to implement, train, and tune the dense variant of DCNAS. So this is something to work on maybe in the future. Yeah, and as I noted before, we save a lot of time, but by not training a discrete architecture from scratch. So we just reuse already trained weights of a supernet, and we just fine-tune them for a few more epochs. And additionally, in the standard DNAS framework, because of the discretization error, there's usually a lower correlation between searching and retraining results. And because of that, if you want to actually get the optimal architecture, because of this low correlation, you would, in the vanilla DNAS framework, you would usually have to run this whole searching retraining pipeline a few times to find the absolutely best architecture. But in our case, we do not have this correlation issue because we do not discretize anything at all. Yeah, so we conducted like a few novel and interesting experiments, which provided more understanding on the discretization error. And in particular, we showed its relation to the entropy of a supernet. And then we proposed a novel searching protocol, which eliminates this issue completely. And although our method does not outperform state-of-the-art methods, we believe that it is a good starting point for a further study on efficient single-stage proxyless techniques. Yeah, and we will probably publish our code very soon. And thank you for your attention.
Thank you very much, Konstanty. So I'm going to open the floor to if anyone has any questions or if anyone has any questions in Zoom. A question that I have first is, so you said that you used the DCNAS search space. Did you investigate any other search spaces for your paper?
Yes, so we start actually from the AutoDeepLab shared space, and then we considered this this goal of training a network in a proxyless way by using just a single stage, and we did not find any other suitable shared spaces other than DCNAS, but maybe there are some. We just decided to use the DCNAS because it's a good comparison for us because it's state-of-the-art method.
Okay, thank you. Does anyone else have any questions?
Or maybe like following up on this question. For example, like the auto DCNAS does not. We can. The idea is that we can train SuperNet with roughly the same hyperparameters as we would train the final network. And in the case of like AutoDeepLab, we would have to use like much lower image crop and much lower network to be able to fit it on the GPU. So the same training protocol shared across searching and retraining makes it actually viable for us.
Okay, thank you. As said, any other questions? Okay, thank you once again, Konstanty. We will move on to our next presentation if you can give me back control.
Okay, thank you. Sorry, how to give you back control?
If you just stop streaming and then mute, I'll eventually figure it out because it's on the other monitor. Thanks once again to Konstanty. Hopefully now my screen is shared again.
My name is Konstanty Sobotko, and I'm going to present our paper.
Oh, sorry, that's the video that I was sent, which has been in. If it's gonna up. Oh, there we go. So next, our next presenter is Tegan, and you're here, and that's great. And let me just get your slides up. Oh, why is it doing that? Oh, do that one. Yes. Yeah, I'll present on PDF. Sorry, there are some technical difficulties. Should hopefully be a few seconds.
Share screen. Share. Share. So, new share. Share. Okay. Now that the technical difficulties are done, I'd like to present Tegan Ann with CycleGAN NAS, which is new architecture search for CycleGAN. It should be recording itself.
So, hello, my name is Taegon An from Korea University, and today I'm going to present about the CycleGAN NAS, which is a neural architecture search for CycleGAN. So this is the presenter, it's me, and I have long hair at that time. I'm from Korea University and interested in automation in machine learning, and this is the homepage. I guess the QR code is expired. So let's go on the motivation. So actually NAS become more and more successful. So for the CNNs and RNNs, and in GANs, and even for the transformers and recently for LLMs, right? So, and at the same time, the neural networks are become more complex. So there are become multiple modules or branches for the multimodal learning, and their objectives are also become so different because they use various like losses or techniques, and more importantly, they are all handcrafted. So we start with GANs. That GANs have two neural networks, which is presented in 2014, I guess. And there are some NAS works that called AutoGAN or adversarial NAS that deals with the architectures of GANs. So AutoGAN uses RNN controllers, and adversarial NAS uses some differentiable NAS approaches. So basically, there are some NAS for GANs, but not for the CycleGANs yet. So there are some more neural networks because CycleGAN is basically a two-paired GANs, and the task is harder because GAN uses an unconditional image generation, but CycleGAN targets an image-to-image translation. So let's go on the methods. So before go on our method, I will explain about the CycleGAN briefly. So CycleGAN is for the unpaired image-to-image translation, and you see that there are images A and B from belong to the finite set A, script A and script B. So note that they are finite, unlike the GANs, because GANs sample the noise from the Gaussian noise because it means that their inputs are infinite. And CycleGAN has three losses called cycle consistency, and one is adversarial, like in GANs, and one is for identity. So it has triple more objective than GANs. And we choose a search strategy called differentiable neural architectures, differentiable architecture search. So typical bi-level optimization in GANs are proposed, but it's not directly applicable to the cycle GANs, because dividing the data set for the GANs is like easy, because for the GAN test and NEST test, they can just sample the noise, but cycle GANs has finite inputs, so it's difficult to divide where. Like if you just give half and half to the NAS and cycle GAN test, or maybe you can give more data to the cycle GANs. Like, so it's important to dividing the data sets. So we are forced to use like single level optimization because it's necessary and also powerful. You can see that the architecture and neural network weights are simultaneously optimized, and it's shown to be working with CNNs, but not in more complex frameworks like GANs or cyclic GANs. So the main concern is that GANs are known to be unstable, and even with the single level optimization, it will be more unstable. So we decided to use the differentiable NAS. We designed our search space as follows. So we avoided to use complex search structures because it is widely adopted and people are giving many efforts on designing the complex cells, but we don't want to do that, and it makes building super networks more inflexible. So we adopted simple cell design based on the ResNet cells, like residual cells. So basically there are some residual connections, and we have two operations, O1 and O2, which has some candidate operations and few candidate operations. I'll explain about it in next slides. So each candidate operation consists of following these poolings or convolutions and interpolations according to its role. Because CycleGAN is a image-to-image translation network, it gives given an image, it outputs an image. So basically, the generator has an encoder cell and residual cells and decoder cells. But discriminator should output a probability, so it just has encoder cells. So let's go on to the experiments. We compared CycleGAN-S and CycleGAN in various data sets. So basically, the original author of CycleGAN provided some 6 or 7 data sets, and we tested CycleGAN-S, basically conducted NAS on those data sets and evaluated on those data sets. So we varied the number of channels of convolutions. You can see the x-axis is the number of channels, and y-axis is the feeds, which is evaluation metric for the quality of image. So the feed is the lower the better, and green one is the CycleGAN-S, and the red one is the original CycleGAN. You can see that in most data sets, CycleGAN-S outperforms the CycleGAN. So let's see more details in the model ratio. So you can, in this table or graph, you can see that for the channel number of 32 and 64, we compare the ratio of models. So basically, the left side is the generator A, and the right side is the generator B. So generator A translates A to B, and generator B translates B to A. So you can see that in most data sets, the size of models are similar, but in the HorseToGebra and iPhone2DSLR, their model size are different. So note that the green one is the CycleGAN-S. You can see that the difference are clearly visible. So we analyze about it. It seems that, yeah, there is a task imbalance. So in HorseToGebra, it is reported that there is an imbalance in the data set. So basically, CycleGAN is an image-to-image translation, and it uses 2 unpaired image data sets. And if you have horse data set and Gebra data set, and if you have more like number of images in horse, then translating may be the difficulty may be different. So we conclude that Gebra to horse is harder than horse to Gebra, and it's currently reported in the CycleGAN author's thesis. So you can see that Gebra appears to be more close-up pictures than horses. So translating Gebra to horse requires more effort. And similarly, in iPhone2DSLR, we can see that there is an unbalanced model. So we can guess that, increasing resolution seems to be more harder than decreasing the resolution. So we see that the model ratio affects the performance. So we adjusted the model size of CycleGAN because actually, if the model size is the whole thing that important, then the architecture like convolution filter size and this kind of things may not be important. So we see the effects. So basically, the brown one is the model size adjusted cyclic N, and green one is our cyclic NS architecture, and red one is they have the same size for the generator A and B. So you can see that adjusting only the ratio is not important. Like it's not enough to deal with the data imbalance. You need to search for the filter sizes and etc. So in conclusion, we build a cyclogenous framework that differentiable NOS for a complex framework called cyclogen. And we used a simple residual cell design, and we use single level optimization for finite data set of the cyclogen. So we see the performance improvements, and it's scalable with the number of channels. And more importantly, we see that cyclogenous, the architectures are able to deal with dataset imbalance. So we observed that it holds GeoGebra in iPhone to DSLR, and especially in host GeoGebra, we found that the previous reports on data imbalance, which is published by the author of Cyclogen. So thank you for listening, and yeah, this is my presentation.
Thank you very much for the talk. I'm going to open the floor to any questions and any questions that were from Zoom. First, a question that I wanted to ask is, as you mentioned that NAS hasn't been used in CycleGANs before, a question I want to have is how did you adapt the current NAS search spaces and NAS methods to a search space that works for CycleGAN models?
Yeah. Actually, I first tried some previous NAS methods, so like using RNN controllers or other version NAS, the search spaces, but it seems that CycleGAN is quite heavy and requires lots of computation. So yeah, I see some codes, but I basically built from the bottom. Yeah.
So do we have any other questions? Okay, well, thank you once again, and we will move on to our next presenter.
Sorry, we do not hear anything.
Correct. I'm sorry. I keep going, right? Okay. So predictor-based algorithms are these algorithms that train a proxy GCN, for example, a graph convolutional network, to predict the validation accuracy just given the topology. And they are then used to narrow down the number of architectures in the search space. During the years, they were very much used because they are super fast, but usually they are used under a single data set, and mostly this data set is Cypher10, assuming that the found architecture will generalize well for ImageNet later. Or recently, some papers focused on improving the generalization ability of these predictors by focusing on different tasks, as in the first paper, ArchGraph, or on different data sets. Differently from these two last papers that I mentioned, we propose again a method to improve the generalization abilities, but we do not deploy an encoder set as in the Meta D2A paper, because although being super well performing, using an encoder set to provide information about the dataset you're working with limits the applicability to only images and not videos, for example. We rather instead use a very simple method, which is providing the vertex shapes information as additional input to the predictor. Then ArchGraph instead requires the tuning of the predictor to move from one dataset to the other. And rather than fine-tuning the predictor, we decided to deploy the validation accuracy of networks not trained until convergence, because we showed that this helps a lot. Finally, as a contribution, we define a new search space, or better, we define a new way of restricting the search space by exploiting the Kronecker product. Going to the search space definition. Okay, so we created a data set, first of all, because the existing benchmarks do have architecture trained on different data sets, but usually they're all data sets that are downsample version of ImageNet. And we wanted to include also something out of distribution, which is fashionableness. So we took the randomly wired search space and decided to restrict it in a meaningful way by exploiting the Kronecker product, which allows you to define two skeleton matrices that you can multiply with random metrics to have a ResNet-like structure. We sampled then 2,000 architectures and trained them for the 4 datasets to get all the measures. In our search space, we did not choose to look for a fixed number of channels because this would have limited scalability, but we kept instead a more flexible approach by defining layers that doubles or half the number of channels. We then trained the networks with the hyperparameters we found for ResNet 18. Before presenting the result of the GCN that we propose, I would like to show you some results on the dataset because they give you an idea of the ground truth and what a predictor can do when dealing with different datasets. So the first question we asked ourselves is, are the datasets that we use representative of the sorting they induce? It's easy to say that ImageNet is more complex as a dataset than Cypher10, but does it hold the same for the architectures trained over a specific dataset? And to answer this question, we analyzed the ranking correlation through the normalized discounted cumulative gain. That is a ranking measures that penalizes more if you rank wrongly highly relevant objects. And key message from the table and from the plot is that if you use the ranking of more complex dataset, you will generalize better than simpler dataset, which goes in the opposite direction of the common assumption. The second message from the plot is instead, if you employ the ranking of fashionableness architectures, you go out of distribution, which justifies the need for benchmarks that involve also different datasets, architectures trained on different datasets. Second question is, do the networks that we have specialize during training? So we again check the ranking correlation of the networks as training was evolving. And key message from this slide is that we noticed that the top performing architectures, which is the dark purple plot, stop changing their rank way before convergence and at a specific moment, which is where we dropped the first time the learning rate. Then we notice from the middle plot that the average performing networks keep changing their rank until the end, and they're very influenced by the hyperparameters. And the worst one are such since the very beginning, which means that in a NAS pipeline, you can use, in this context, the validation accuracy of networks not trained until convergence. And as you can see in the third plot, the predictor will still be able to rank correctly the networks. So given this, I will show you quickly some results. So we trained our GCN in a binary fashion, meaning that we do not predict the validation accuracy, but we rank the networks. And we gave as input the topology of the networks, the encoding of the layers as usual, and as in addition, the vertex shapes. So the shape of each layer normalized with respect to the maximum shape that we had. And we decided to use floating numbers and not one-hot encoding to have a sense of distance between vertex shapes. And then we trained the predictors with the validation accuracy that we had at epoch 40 and not until convergence. And basically we saw huge improvements, especially when fashion MNIST was involved. And also when without distribution shift. Compared to other approaches, we again saw big improvements in terms of fashion MNIST and Cypher10 especially. And before concluding, I want also to spam a little bit another paper that is in the main conference, that if you're interested in new architecture search, you can pass on Wednesday to my posters. And thank you.
Thank you, Sophia, for a great talk. Again, I'm going to open up the floors to any questions. A question I want to ask first, though, is you mentioned the use of different data sets apart from the typical standards of Cypher10 and ImageNet. A problem that me and some colleagues have identified over the past few years is sort of reliance on these two data sets. It seems that in your work here, you've seemed to have identified a similar problem where using different data sets is better. Do you think there needs to be more of a push for more data sets?
Absolutely. I think that there should be more benchmark for NAS in general, not only related to images, but also, as I was mentioning before, to videos, for example, because most of the approaches are related on these benchmarks and you need them to be fully comparable. So yes, I guess that would be a good direction.
So do we have any more questions? I think I thought I saw a hand earlier.
So we use the 3-layer graph convolutional network. So the GCN layer was defined mathematically in a paper from Welling, and we simply stack 3 layers. It's super fast to train and takes like for 2000 architectures roughly 2 minutes.
Okay, thanks again, Sophia, for your presentation, and we'll move on to our next presenter. Okay, so I'd now like to introduce Chusun Chen with his paper UpNAS.
Yeah, thank you, and good afternoon, everyone. And the title of this paper is Unified Proxy for New Architecture Search.
Doesn't often, it's not showing present. Why is it not doing that? Should work.
Oh, okay, thank you. Yeah. Okay. So existing NAS approaches can generally be divided into 3 categories, including multi-shot, one-shot, and zero-shot. However, the multi-shot and one-shot NAS would be take a longer time for training. And so the zero-shot approach, however, it can lessen the computational burden, but each proxy performs often well for only specific data sets. So in this work, we hope to unify multiple zero-cost proxies. Yeah, since a single zero process aim to accurately calculate the quality of an architecture without the need of training, existing proxies can be roughly divided into two cases, gradient-based and gradient-free. In our work, we propose a general method to combining multiple zero-cost proxies to form a new zero-cost approximation. And in the current study, we developed implementation of zero-cost proxies by NASLib, including the following kinds of zero-cost proxies. And but our approach can be done for other kinds of zero-cost proxies. And our NAS start from the issue that no single cost proxy is suitable for all benchmark data sets. And so how do we can combine existing zero-cost proxies and yield a more powerful zero-cost NAS, zero-shot NAS? And our method is simply combines different zero-cost proxies by adding them with a set of a fixed combination weights. That is a linear combination, and the approach is easily scalable. And for example, when we combination of n zero-cost proxies, the combination coefficients lambda 1 to lambda n are learned based on a small existing NAS benchmark. For example, we only use the NAS bench 201's CFAR10 subset for learning such kind of linear combination, and then allowed to be used for other unseen architecture spaces. And our approach is called MPE, multiple proxy estimation, an estimator for multi-way zero-cost proxies. And the method consists of an architecture-to-vector, ARC2-VEC encoder. That encoder network requires no ground truth accuracies, but can simply perform an architecture to vector using only the topology of the network. And then we have a simple multi-layer perceptron to estimate the scores based on the M proxies. Our steps include the following three, and we will introduce them in more detail. So for the architecture to vector part, we adopt the implementation of the VGAE approach. Yeah. This approach can transform the architecture search space into a continuous embedding space. And however, currently this method is only operable for cell-based approaches. So our approach is also cell-based. And it represents itself as a DAG and denote architecture with the topology graph of verticals and edges. And it will use the upper triangular adjacency matrix A and one hot operator matrix X to encode the cell-based neural architecture. And so by using this approach, the objective of VGAE is to optimize by maximize the variational lower bound in below. Okay. So more details can be found in this paper. So use this method, we can get the architecture embedding here. It consists of an architecture encoder and a decoder. Then we simply use this encoder to end the embedding and perform a gradient ascent search over the embedding space. And then finally we'll convert back our found embedding to the using the decoder to the search architecture. Okay. So in our approach, we only require zero cost proxy scores to train our multi-proxy estimator and not the precise accuracy of the model architecture. So in our training phase, we assume that the architecture encoder trained by VGAE are available. And then so for any architecture, it can leverage this encoder to convert the architecture into an embedding. And so in this embedding, and we design a simple multi-layer perceptron, only three layer perceptron. And this MLP aims to learn the predict scores that approximate the zero cost proxy scores. For example, here we are many zero cost proxies that have been proposed by many previous papers. And so we use these proxies, zero cost proxy scores as supervision and learn our MLP. And so that we hope that for the input architecture, the output predict score can be highly approximately to the these zero cost proxies. And in our implementation, for training the MPE, multi-proxy estimator, for the NAS bench 201 space, we take 50% of the architecture together with their proxy scores, zero cost proxy scores. For that space, we generate 10,000 samples for training the MPE. And here we also have the how to linearly combine the zero cost proxies. As we have mentioned, we will provide a fixed weight lambda 1 to lambda m to combine these m zero cost proxies we used. And how to find these m parameters? As mentioned, the combination parameters we are learned by using based on only a very small subset of the benchmark. Here we use the NAS bench 201's CFAR10 subset only. And the optimization criterion we used is Kendall's tau. That is an order preserving loss, to find such kind of a weight. And then once the weight are find that they are fixed, and then so these weights are fixed. And finally, when those are all done, we can then perform the architecture search on the continuous architecture embedding space simply through gradient ascent learning. So that's this part. So our entire goal is to maximize, to find the architecture in the embedding space, to maximize the that kind of a weight has been computed and fixed, to maximize. These are the zero cost proxies they are totally zero cost proxies we use, and then we want to maximize this goal simply through. In fact, this is simply through gradient ascent. Yeah, so it's very fast. Okay. Yeah, after finding the architecture in the continuous embedding space, we use the decoder part of the architecture to vector algorithm to convert it back to an architecture. Okay, so the details of the proxy weight lambda, as we mentioned, we use the TPE to search for the weights, maximize the rank correlation using the NAS bench as 2001 CFAR10's validation accuracy. And that's the ways we found, and we also do some quantization and have 4 kinds of such kind of combination weights. and they are then fixed. And then we have also used our MLP, multiple layer spectrum, to find an approximation of many zero cost process, existing zero cost process. So by combining that, we do the gradient ascent, to find the architecture in the embedding space. Okay. Here are the rank correlation we found by our NAS method with several kinds of combination weights. And as can be seen, the rank correlation are all higher, than the original zero cost process that have been combined. And to evaluate our performance, we use the NASBench 2001 search space and also the Dart search space. The above one has the ground truth for every architecture, but in the Dart space, there does not have the exact scores for all the architectures because the space is too large. And first, we evaluate our NASBench, our method's performance on the NASBench 201. And the left part is the comparison of our approach to the zero cost process or training-free approaches. As can be seen, our approach is competitive that can find a little better architecture than the other process, zero cost process or training-free approaches. And for the comparison of a non-training-free approaches, our approach is also very competitive. Although a little worse, but the approach is training-free. Our approach is belongs to the zero cost process approach without using the model, without using the training. And later we have done our approach and for the search on the ImageNet. And to do so, because ImageNet is too large, so we simply perform our gradient ascent search. This one has been done in the Dart space. Dart space is much larger than NASBench 2001. Okay, and so to perform the results on the ImageNet data set, we first search on the Dart space based on the CIFAR10 data sets at first. And then the architecture, the best architecture found based on CIFAR10 are then applied to the ImageNet data set. And the performance on the ImageNet set is here, and in fact, it achieves very well the results on the Dart search space for the ImageNet. Here are our results, on the ImageNet. Okay, and the search time is also very short. And that's the architecture we found for the Dart search space, because in such kind of space, there are two kinds of cells, a normal cell and a reduction cell. That's the architecture we find based on the CIFAR10 data set and applied to the ImageNet. Okay. And the ablation study of the search strategy, if we perform the ablation study on the CIFAR10 based on the Dart search space. And if we use gradient ascent, continually search in the embedding space, the performance is the best compared to using the evolutionary search or random search. and the time is also shorter. Yeah. So the conclusion is that to our knowledge, no single process works for the best of different tasks and scenarios. We thus propose unified process for NAS. Is a generalized scoring function, and realized by architecture encoder. That's simply based on the network topology. Yeah, such kind of decoder, and design a multi-layer perceptual learning to predict the multiple zero cost process, and then unify them. Okay, and we show how to find new architecture through gradient ascent. Yeah, in the experiments, the method achieves competitive performance and significantly reduce the computational resource required. Okay, yeah, so that's our UpNAS work. Yeah, thank you for your listening.
Thank you for your talk. So we are running a bit behind time, but we should have enough time for a question or two. One that I did want to ask is your fixed weights of the proxies. You in the presentation you said you learnt them from Cypher10. Were those weights that were learnt from the Cypher10 applied to the ImageNet experiments, or would you do a short train to find the weights for ImageNet?
Okay, we do not do another training, but the fixed weights we have, original weights we have quantized them to 1 or 0. So there are 4 different kinds of versions. Yeah, we do it by using 2 versions. Yeah, and one achieved the so far maybe the best performance on the ImageNet for the dark search space. Yeah, and the other also very, very high performance. Yeah.
Okay, thank you. Does anyone else have a question? Okay, no, in which case, thank you once again, and we'll move on to our second off last presenter.
Here we have a sequence of inputs, and even we use original screen text, is obviously still generate and that context is not really used. And upstream cache is a natural advantage. That is, you can directly leverage each of them into the generating and previous frames. As you can do with previous symmetry, that is using the recent information. You can see when the sequential inputs comes in, you can leverage the future frames.
Okay, so I would like to introduce Tunho Zhang with his paper on CSCO.
Thank you, David. So, hi everyone. So, today I'm going to present my work, the connectivity search of convolutional operators, and this is the work that I completed when I was doing the PhD at Duke University, and this is also a collaborative effort of the Athena AI Institute, the Duke University, and also the University of Houston. So, oh, sure, thank you. So before we dive into the detailed approaches, let's try to figure out the background information and also the motivation to do this work. So we know that the CN architectures, they're enriched by the dense connectivity of different convolutional operators, such as the one-by-one convolutions or the three-by-three or even the depth-size convolution families. However, we can see as the direct acyclic graphs can be the most effective tool to reflect the structure of the CN architectures, because you can simply say that a CN architecture is composed of various directed acyclic graphs, whereas each directed acyclic graph, also known as a DAG, has a building cell with like different connectivity and also different topologies of the convolutional operators. So in this work, we are going to study how to effectively search through a directed acyclic graph and how to use a search algorithm to seek better architectures while we are going to scale this stack bigger and bigger, and we are going to scale the search algorithm to more like data efficient and also search efficient scenarios. So our approach is based upon the predictor-based search, and let's first try to revisit the predictor search mechanism. So the predictor-based search algorithm has two phases. The first phase is that we are going to sample different architectures to try to map the architectures to performance using a predictor, and then we are going to use the predictor as a surrogate model to try to probe the whole search space and to identify the best architecture. So there are actually two phases. The first phase is a sample phase, and the second phase is a search phase. However, upon the search within these two phases, there are a few challenges within the predictor search. The predictor-based search mechanisms. The first challenge is the insufficient efficiency when we are going to grab the architecture performance pairs to try to train a predictor, because each time you are going to sample architecture, you will have to train them either on a proxy or you are going to use the full training pipeline. This is going to introduce some extra cost if you are going to run it on hardware. The second challenge is that the suboptimal ad hoc exploration using the predictor during the search phase, because if we are going to scale up our DAG to compose of like multiple nodes, let's say 12 or like even 16 nodes, compared to the 4 nodes paradigm in the DAS, you will see that even if you have a perfect predictor, it's very hard for you to utilize this predictor and try to find the most the most effective sub architectures within the search space, because even you can try to curate the performance very quickly. You have like too many candidates to choose from, and it's very difficult for us to use existing algorithms to reach the local optimal solutions. So to address these two challenges, we have actually proposed our paradigm to try to utilize the connectivity search and try to introduce two technique approaches to make better efforts and try to leverage and try to address all of these challenges. The first approach is the graph isomorphism. So this is actually intuited by the observation that the isomorphic graphs, which means that the graph that represents the same architecture in reality, they actually will always end up with the same performance when they are going to evaluate on the same training pipeline. So intuited by this observation, we can see that within our search space, there are like multiple nodes representing the same operators, such as the one-by-one convolutions, such as the Sylvester depth-wise convolutions. And if you're going to convert the single graph towards an isomorphic graph, like using the swap or using the permutation of the adjacency matrices, you can actually end up with the same isomorphic graph without the need to try to train the same architecture on the hardware and try to obtain all of the metrics. So in this way, you can try to save the computation cost by trying to introduce the isomorphism as a data augmentation for the predictor. And when you're going to do this, you can achieve better sample efficiency during the sample phase of the predictor-based nest, and you can use this to improve like the ranking correlations of candidate architectures within the search space during the architecture search algorithm. The second technique is the Metropolis Hastings evolutionary search, which is an improved version of the regularized evolution. The idea behind the MHESE is that during the regularized evolution, we will typically accept the stronger evolutions or the stronger mutations because we deem that this is actually better, and we are going to keep it like within the whole population to try to evolve towards better solutions. However, in the MHES, we define a more quantitative approach to try to accept the weaker solutions within a certain probability and try to use the temperature to gradually annealing the search process and try to evade local optimal solution for better candidates in discovery. Note that the proposed MHES will generalize the local search, which means that you're going to perform a random work like along the whole search trajectory when the T is going to achieve 0 and is going to achieve the same level of performance as the evolutionary search when T achieves infinity. So actually the annealing algorithm on T will guarantee you a better performance compared to existing search resolutions on the very large scale depth search problems. So these are the two techniques that we propose to try to address the challenges in predictor-based nets for the large-scale DAG search space. And we perform very detailed experiments on image1K benchmarks and try to compare the results with like all of the Dust family architectures, and we can see some like very noticeable gains on the image that 1K top one and also the top 5 with a very plain training pipeline. So when we are going to perform our ablation studies on the Silverton, which means that we are going to evaluate the effects of the MHES and also to compare with different search, like different search strategies, we can see that the combination of the graph isomorphism and also the MHES will give us the best results on the Silverton, whereas here we are using a pipeline that ResNet 20 will achieve around 92. Another thing that we would like to note is that we're seeing this very large scale DAG-based search space. The random search does not have a very satisfactory performance. One thing you can see due to scale and due to the heterogeneity, random search is even harder to come up with a better architecture compared to ResNet 20. Whereas with some of these techniques, we can find something better. Especially so we still expect that we can try to deliver more efforts into this scope and try to better enhance this algorithm. So for the people who come out with the research, we basically open source our implementation using the using the video understanding task. Our code, and we hope that here in this presentation and thank you very much for attending today's session.
I think for me, really, the main thing is that video generation probably is very different from like video classification. They actually do need to have some understanding of motion, understanding of temporal coherence, consistency, all of that. I think that is why probably in the next few years we actually are going to see these models be the ones that develop very consistent video understanding.
How generalizable do you think your method would be to other data sets?
Thank you for the question. I think that for the generalizability of the method, I currently do not see any constraint because we can simply replace the node to any kind of operators that you can think of, and once you figure out how to do the projections, how to do the concatenations, I think that this method can be generalizable to not even image that, but also you can try to do some other vision tasks like the segmentation, like the post estimation or something else. I see the only limitation is that because on Silverton or image that the proxy task is quite mature because, for example, if you downsample 100 classes or if you reduce the number of epochs, you can typically get a very good correlation with the ground truth pipeline. However, if you're going to scale to like more complex tasks, maybe we need some efforts to find the better proxy and try to improve the search efficiency because the scale actually requires many samples, and even with the augmentations, sometimes you cannot resolve like such like 1 magnitude larger examples in augmentation. Yeah.
Okay, thank you. Do we have any other questions? No, in which case, thank you once again, and we'll move to our final talk of the session. I'll just get that up. But unfortunately for our final talk, the speaker is unable to make it today. However, they have provided a video recording of their presentation, so we'll play that now.
Hello everyone, I'm Tim Shaw from Group. It is my pleasure to present the paper on optimization where your architecture search for efficient deployment on mobile device. Convolutional neural networks are widely used in mobile AI scenarios. However, mobile devices usually have limited resources. Convolutional neural networks need to be carefully designed within context.
Okay, so I mean, apart from content creation, I think content creation is probably the most obvious application right now. I think probably it's also going to come down to, I would really like this. I don't know if somebody will make it. Hopefully somebody does. Is like when you want to
you like, I think today if you want to, something breaks, so I don't know, your refrigerator breaks or your washing machine breaks and you want to repair it, you go to YouTube, you try to find out, okay, LG model SK300, whatever 9129, how to fix the door. I really hope that basically we get to a point where right now ChatGPT, if I ask it like, hey, I want to do this, or I ask any LLM, it'll give me a bunch of steps, but it's not really grounded into what I really want there. I hope that we're basically able to get to a point where media generation models are so seamless that if I basically ask it a question that click a picture, or I have the Ray-Ban glasses, whatever, ask it that, well, how do I particularly like fix this? It's actually able to walk me and generate all the video of how I'm supposed to go and fix it for that particular location where I am, or if I'm stuck at a particular thing that I can't find the screw, or I don't know which particular board to move or so on, it actually helps me do that. I hope that finesse. So for me, that is really, apart from content creation, that is really the thing that sort of melds together the understanding piece of it, because it really needs to understand what I'm trying to solve and what the object in front of me is, and then sort of is really generating to a fidelity where actually can reason about different types of bolts and like how they need to move, or like moving on to like other applications of this sort.
Here, we more clearly demonstrate the differences between our method and the existing methods. When training the context networks, fake quant operators are employed to simulate the composition. Existing composition awareness only contests the input and weight of the operator with large flows, such as convolution flows. Another class, just as batch normalization and pooling layers, may be deployed. So only the count layers of the deployed subnets can perform intake calculations. Other layers still with floating point calculations. That's why the existing methods result in limited latency reduction. For our method, during SuperNet training, we consider the optimization during deployment, such as count BN folding, and we ensure all the layers are fully compact. So the count BN layer can be simplified to a context count layer during deployment, and the whole subnet can perform intake calculations. However, simulating the deployment behavior is challenging. A standard strategy to simulate diffusion of convoluted BN layer in standalone context network zone is to merge the wing of count with the moving average statistic of BN layer. In SuperNet training, this will bring two problems. Firstly, we plot the cosine similarity of moving STB from 100 random sample subnets. As can be seen, for different subnets, the moving STB vary greatly. It is impossible to update moving STB separately for billions of subnets. If we only update one moving STB of this SuperNet across all subnets, it will mislead the direction of SuperNet optimization and result in non-convergence. Secondly, the scale value S that maps the floating point value into fixed point value plays an important role in improving the accuracy of context model. Due to the differences in moving STB between different subnets, BN calculation is required to recover the performance. Different moving STB across different subnets means that the folded length of each subnet is different. So the optimal scale of the same layer of each subnet is also different. Meanwhile, we cannot string different scale value for different subnets because the amount of subnet is large. If we train a shared scale across all subnets, the search result based on a mismatched scale will lead to non-optimal results. To tackle the problems of non-conforming unit training and non-optimal searching results, we proposed Optimus. During training, the proposed framework jointly trains the scale predictor with the SuperNet under a batch statistic-based training strategy. During search, The scale of each subnet is calibrated with the self-predictors after VM calibration to improve the performance. In this manner, the proposed framework is able to find the optimal context architectures can be directly defined under different resource constraints without the chain. Now we present our batch statistic-based training strategy in detail. Our goals to simulate the deployment behavior of subnets during supernet training, which means we need to find an accurate proxy of moving as speed of each subnet during training. Here, we randomly select 50 iterations during supernet training and show the similarity between batch speed of supernet and the moving speed of the sample subnet in this situation. It can be seen that moving speed of different subnet is much similar to the batch speed of supernet than the moving speed of the supernet. Based on this investigation, we propose a stable batch statistic-based training strategy for context supernet. Instead of folding the moving speed of the supernet, we fold the speed of the target batch into the sample weights. The same composition takes the folded weights as input, and the shared convenient layer is used to a single conveyor to simulate the influence behavior. The proposed predictor effectively calibrates the optimal for scale value for different subnets of the VM calibration. For the convenient layer is input activation X and output activation Y. Before fusion can be formulated at this equation. Supposing each element of sigma is sigma 0 and each element of gamma is gamma 0, then the optimal scale after folding is the original scale. We multiply gamma divided by sigma. Unfortunately, the value of each element in sigma or gamma is typically different in the network. Therefore, we predict the optimal scale with a linear transformation of gamma divided by sigma, as shown in this picture and this equation. For a well-trained compact network, fixed to be deployed. Scale S and gamma are fixed value. So we convert the scale predictor by merging gamma and S into parameters theta. The converting scale predictor can be directly at the SPD statistics into the optimal scale. In this manner, the proposed scale predictor can learn a more flexible transformation.
Yep. So I think my perspective on this is very similar to like when I remember I was maybe a few years ago when AlexNet had just come out. Maybe it's like now old. But at that point, it was like, okay, academics cannot train AlexNet on ImageNet. This is like too large scale. This basically can only happen in 4 places in the world or three places in the world. And so there's absolutely, I don't know, what are PhD students supposed to do? I think it's the same thing, right? Then the progression was that, okay, there were a few people who trained at Berkeley, the original cafe like AlexNet or CafeNet models that came out, and then basically everybody was trying to fine tune them, get a grip on understanding what these models are, but really people were not pre-training on ImageNet. Now it's common, and now like when Junyan's saying that, hey, we can just do ImageNet, but like, yes, 10 years ago, that was not the thing, right? So I think it's going to be the same thing where right now, yes, I think most people are not able to train it from scratch because it's a very resource intensive process. Large models of today are tiny models of like 5 years from now. So I think like that's basically going to be the situation anyway. So in general, that does mean that we should not stop basically working on it just because industry has the resources to train it at scale today. It does not mean that's going to be the only thing to do like 5 years from now. 5 years from now, everybody will have the resources to basically train at least some version of these models. And I think the second thing to Junyan's point, yes, where I think a lot of the innovations, I think industry is really good at scaling things, but it's hard typically to like go back to the drawing board and rethink and basically like invent a thing completely from scratch, which has no evidence at all of working. So essentially pie in the sky ideas. I think that absolutely has to come from academia. That's actually where like most of the industrial ideas do come from. I think even taking these large models that have been released today and understanding why they're working, it's a huge challenge. I think there's a lot of theory about these models, generative models, either continuous space or discrete space models, which we don't really understand, which I think it means even at a small scale, you can actually do a lot of like work to understand why these models are working or what is really making them tick. So the scale aspect is really to just like create these impressively
So once
amazing
again,
images. But I
since
think
the
the
speaker wasn't
understanding
available to
aspect
attend
doesn't
today
really
at the
need the
presentation,
scale to go
we're
with it.
gonna skip
And
questions.
yes, if you
which,
work on it now, like 5 years from now, you can actually
will bring
also
us
tackle the
towards
scale
the,
aspect
end
because
of,
that model actually
this
becomes
workshop.
reachable
So
for
I would like to
everybody.
thank all of our speakers again for presenting their work, also our keynote speaker. Before we close, I'd like to remind everyone that we have an upcoming competition. In previous years, we've run an unseen data competition, getting NAS methods, having people design NAS methods without knowing what data they're going to be evaluated on. And this year, we're going to be running it at AutoML in September. We're expecting to move into phase 2 in the next 2 weeks, where you submit your algorithms to us to make sure that it works on our benchmark. There's still time to take part, so if you're interested, please join our mailing list or go to the website to download the starting kit. Thanks for attending. If you want to talk to us about NAS, please get in touch. You can contact me at d.towers2@ncl.edu.uk. I will also be at the conference for the rest of the week. And stay up to date with future workshops or upcoming competition, sign up to our mailing list or complete our form. Thank you.